Okay. Okay. See, yes. Let me test this first. Connection. Okay, good. Hello, everyone, and welcome to today's live stream, where we will be exploring some of the ideas we had talked about last stream. And looks like I have bad connection. Okay, not good, not good, not good. Okay, let's try this. Let's fix this first and try again. Okay, let's try again. Anyway, I'll just keep going. Hopefully you guys can hear me and you can see my screen. Okay. Awesome. Okay, great. So yeah, we are continuing with our model. We've talked a lot about and we've done a lot in the model, and so far so good in terms of trading and in terms of everything we've been exploring: plasticity, event modulation, and then we also talked about online learning in the previous weeks. So I won't go into that. For those who are curious of what we talked about in the previous weeks, you can easily access our live stream for the previous one. So I have created a playlist for every live stream we've done. It's called Live Science, where you can access those live streams that were past. But for now, I just want to talk about what we are heading into and what we have done. And by what we have done, I mean, like, the model works, but it doesn't. It does work with it doesn't work with real tests, right? We haven't really tested the model on a real tests. By real, I mean like some task to work on. But to do that, we have to go through each of these step by step, figure out how to make each of them work, and then how to see the results. Is it improving? Is it not improving? Is it working as it should? Is there something we should be doing to the model for it to perform really better? So those are things that we'll be talking about today, and I'll show you some results that I've been like tinkering around with last week. I think, yeah, last week. You know, the result, talk about the results, and then, but the title of this talk stream is multi-model or multi-agent. So multi-agent cultural evolution, cultural dynamics, all the stuff that are involved in culture. Those are what we'll be talking about today. And by culture, I mean, we know about memes. We know about how memes spread from one individual to another. Good memes tend to survive. That is sort of like natural selection of meme world. So good memes tend to survive, go on to survive longer, and the idea of meme is really just about ideas. I mean, idea of meme is really just about ideas. So yeah, they are just ideas spreading from one person to another, and these ideas are usually um, they are like things that our human brains generate. For today, it's different because we live in a world where we have introduced a new agent or a new species called AI. So we have to talk about memes in a different format. It's not really about like how humans used to enjoy memes, because they used to really just be a human thing, like ideas from the human brain. Now memes are everywhere, and some of them are AI, some of them are human, and it's hard to tell which is for human and which is for AI. And one of the ideas, this being one of the ideas that has has led to faster spread of ideas in humans. Literally, like the word meme means ideas, the original meaning by Richard Dawkins. But why is it important for this idea to be explored further when we talk about cultural evolution? Because culture has really been our a driving factor in terms of since many years ago. So it has been culture that has led people or us to evolve, because we spread ideas through many means. One of them is language. The other one is, now it's just memes, and then we have people writing papers and books has been just spreading ideas. Even music is one of the many ways of spreading ideas. Now, why are we interested in this, and why this project is specifically interested in the cultural dynamics or cultural evolution, is because think about how agents can evolve through other agents' ideas, or in our case, through other agents' code. We have code, and an agent runs through code, and then for our case, we have what we called. I talked about this. The parameters we call the code, the Z parameter, which is a compressed version of the agent's code, right? Now, this is in a sense what we call ideas. So, or you can name them code, or you can name them genome, spreading genome from one agent to another, or you can even call them rules. In a computational world, then we talk of rules and how these rules can be used with other agents. And the best rule is one that reproduces what you expect, or what you want, or the goal, right? So if there's a best rule, you can spread that rule to different agents, and then they use it. They generate whatever they want. The rule says, and then keep doing that until we have like the best or elite agents at the end of the training, or at the end of the evolution process. And those elite agents say shares one major rule or meta rule, which is now used for the entire system. Now, that's one of the ideas we have. That's one of the idea we have explored, and we have built a system that uses this idea called memetics. So I'll just pull my browser and search for this. So memetics is a strong idea. It's the theory of cultural evolution. So it's a theory of the evolution of culture based on Darwinian principle, with a meme as the unit of culture. So meme is the unit of culture. In this case, it's the currency for this evolution to happen. So not really just currency. Just currency sounds like it's the only thing, but genes are like one of the main thing humans spread ideas, right? But in this case, Darwinian principles explores these meme idea, and then culture uses currently meme as a way to spread ideas. So the term meme is coined by this guy, and then Richard Dawkins in his books, The Selfish Gene, to illustrate the principle that he later called universal Darwinism. Darwinism. What the hell is this? Universal, also known generalized Darwinism. Darwinism. Universal selection. I see. Okay, so all evolution process depend on information. Very important. There has to be information. So this memetics idea, and if you see from, let me just show you the code. If you see from the code, I have this. Let me find it. Plugin should be somewhere. Memetics. Come on, are you doing this now? Like, you don't. Oh my god, my editor just stuck for some reason. Okay, let's try again. So memetics. So this is I have the entire code scoped out for everything. So I have this class called memetics, which is generally handling everything about memetics. You just pass it the configuration of memetics, and I'll show you an example of the configuration. What's happening? Is it am I running out of memory or something? Okay, so yeah, so memetics. So this is the example configuration of what memetics entails. So we have outbox length. So this is the thing that you give out. So you send out information. That is the amount of information you each agent has to send is 256 bits, right? We only send 256 bits, and then the amount of information the agent receives, that I'm talking about not just any information, but novel information, like information that is legit, if you like. And this is the same as outbox, and so the main thing is just inbox and outbox, and then every other thing uses the inbox to fill in which information has to be sent to another agent or received from another agent. And these plugs just do the the measuring how much information is legit, or in our case is novel. Just good information, or information that adds value to my existence, or to my exploration in the environment. And then value of information is also measured. So we measure the value of information using these metrics. And then once we have everything set up, we use exchange, run agents in parallel, and then exchange information while they do the training. Now that's one of the ideas we have explored and we will explore. But I just want to show you some of the results we have. Like I would say in okay, so I want to show you this. So before we got into the deep, like training different agents in one go and seeing the results, comparing them, I want to just give you to take you through these steps, the first 3 steps, where we had to structure the system in a way that we can evaluate our results, and talk about training, compare the training with evaluation, and see how generalized or successful the models or the agent is doing. So this is so I talked about last time how we will be doing this, and one of it is evaluation versus training separation. We separate the training from evaluation, and every n episodes can be like you can divide n. If you have a run of 20 steps, so 20 divided by n, you do that every n step episodes, but that's what we call episodes or epochs. Run 5 to 10 deterministic episodes, no exploration, no learning, and plot evaluation. So this is what I want to show you today, and talk about mimetics, and then success rate. We will measure success rate. We would set a threshold for how to measure success. I mean, I have done this, so I just want to talk about the results. And this makes improvement obvious even if training is noisy. So our system, as we have talked about, as we have seen, it's quite noisy. This is richer environment, so our previous results have been telling us that the system is noisy and it's non-stationary, and with such a system you want to train, yes, but you also want to know how well can it perform when not learning or exploring or doing anything else, right? So I'll show you results for that, and then generalized test. By generalized test and evaluation, I'll show you how we have configured the system. But generalization test is like, have a test, 100% training, or location, in our case, just location, target locations, because we are dealing in a rich environment. We have to know coordinates for the agent in this environment. So those are what we're calling target locations, and 70 of them for training, and then we can evaluate 30% of these for evaluation, right? And then report success. And then the next thing we will do is adaptation, regime shifts, randomly change dynamics per episode, and then we can do like jumps, jump every, you can give it a number like m steps, jump every m steps, then measure the recovery. So can it recover? What it means is just that if an agent is doing so well, or if an agent is going badly, can it recover in the next 25 steps? You jump to the target steps. So can it recover in 25 steps? If it can it stay in that recovery spot for long enough, or for the entire run as it improves? So that's what we're calling adaptive or adaptation in regime shift. So every time system shifts, we need to measure how it recovers, or how it stays when it recovers. So that's one of the things we'll do. And so okay, let me open this up. Hopefully my editor doesn't misbehave again. I'm not sure why it's doing that. Let me try to find out. Maybe get rid of these. still shouldn't do that. Anyway, so culture. Oh, sorry, not culture. Okay, culture has occupied my mind. Talking about evaluation. Okay, so evaluation and training. We have a way to measure evaluation. Okay, what is happening? Okay, reload this. 70, 67. There should be a 67 somewhere. Yep, there you are. So 67 is the latest run, and we have episodes, and then we have evaluation, then logs. Logs is just everything, and then adaptation. Now I have the plugs. So from the right, I have this evaluation, call it eval. When enabled, we evaluate during the run. So we turn off everything else. By everything I mean learning, noise, everything. We turn off the system, and then do what we call clone the system so that we can evaluate from that. So this is and by clone I mean just you're running the system, but we're using flags or this enable no learning, and no learning. If no learning is true, then we are in the evaluation stage, right? So we just know that from this stage we don't do any sort of learning. And by another thing to know cloning is the system uses seeding, right? Seeding is this value. So this value is I've never changed, so it's 42, but the seed is controlled randomness. So how random the system is. So if we set the seed for the training, which is 42, then when evaluation we this is like a hack, so we don't clone the entire system and then run it. We just set a different seed for the system, but the system will run, yes, continue running, but it will run with sort of different nature, or different, like it would not be the same, right? Because the seed has changed. So different seed, you can put any seed value right there. And then same for generalization, same for regime shifts. And then we can also go down and see target jumps. So target jumps, as I said, is we want to know how adaptive the system is, or how it recovers when it's going down. So these are the new configuration. And then what I will do is, so it's just we're just running the same thing, like we're doing the same run as always. We don't do any sort of change in the run. So by any run, like same run, same process, we're training in training run.training. So run.training is let's find that. So run.training. So this controls the run. So I've talked about this. I don't know why I'm repeating, but nothing has changed in the code in that section of the code. What we just have is plugs for this training. Now, I just want to show you how the system is behaving currently, and see, like, from what we have, how can we make it better, right? So one thing, I would just open this first of all. Let's see. supposed to be somewhere. No. Images. I'm looking for images. Yes. Okay. So yeah. So I'll start with maybe distance plot. No. This is adaptation, recovery, returns. This is too much. I think I will. Okay. So these images are generated by GPT. So let me just give open this and put it somewhere so that we can see what I'm talking about, like how it generated this. So I gave it the data, and told it to do some analysis. I'll use the latest. So we are gave it the data and told it to analyze, and then generated these beautiful images we can see here. Let's start with success. I think success is most important, but yeah, we can also generate our own using these Wolfram language plots, but I will show you these ones because they look nice, I think. Yeah, and success threshold is 0.05. That's just how we measure. We tell it this is when you are successful, but this value can change dynamically when the system is running. We don't have to tell it like, I mean, it doesn't have to be fixed, right? It can be fixed if you want to, but we don't have to make it fixed. So this is the as you can see, it's not like doing so well in terms of like how training plus or eval. So eval main and eval success final. So eval success final is this red one. So red one, and then we have the train success. Oh, let me make this big. It's confusing. There's so much graphs. Hopefully you can see my cursor, but this is what I'm looking at. So the red one is the final how the system generally did after the run, the entire run. Then training success mean, and this is like a window of 50. We have trainings. The training is the blue one. So we run the training, and then measure using training success final. So training success final is the orange one. So the orange one is this. So the final is down, and so as it's not okay. I mean, not okay. It's not performing so well at the end of the run, right? Like final is way down there, and it started off up here, right? So what we are seeing here is that final success is not really matching up with the training, right? But it's trying, and every time it tries to, like, recover, it never really stays or recovers and stays there. That's why you see like so many blocks, so many jumps, so many. It's everywhere. It never recovers and stays at recovery position. It never really, once it goes down, maybe stays a bit and then just goes up again. So like recovery is quite bad in the final final success. Now that's just success, and I think we should have we should also plot this threshold somewhere, because that will tell us if it's okay. So the threshold is here, 0.5. It's around here. So this is this threshold, and when it's above threshold, it's doing really bad. So the green one, is bad, it's doing bad, that is when the minimum of the green one is the minimum success. That's doing so bad because it's above the threshold. And if it's below or at the very spot, the very exact position where threshold is, then we're doing okay. But generally, the system is not. We still have some a long way to go, and then I'll also show the distances. Distances. This is the latest. Yeah. Distances is another one. But yeah, so I'm not doing a good job of explaining this, but we will see how our ChatGPT really analyze the data so well. But let's talk through this. And so the blue one is the training, and we have orange final. Orange is the final. Distance rolling versus eval median. Eval is median green, and median final is red. Yes, this is different from the last. Okay, because it's distance, but yeah, success threshold. I think we have success threshold here. So the threshold is 0.05, and everything is above 0.05, which is not good. Like, it just says that the system is not performing so well, right? So looking at this, it just tells us that we have some maybe it's just because we ran for 20,000 steps, but I haven't run for a lot of steps to see exactly how well it performs in the future steps. But still tells us that we have something to do. We still have a long way to go for it to really do some real world tests. And but this is the path to the real world test. So once we have a way to evaluate the system, how it performs, then we can try to run it on a real world test. Now here's the recovery. So this is the adaptation, and how well it recovers during training. If it's down, how well it recovers, and how well it keeps the recovery. If it recovers, how well does it keep that recovery spot? Now the blue is training, and then 20 train epochs or episodes, and then recovery after jump. So after jump is, by jump I mean after you do some shift or regime shift every 25. I think I'm setting it to 25 if I'm not wrong. Regime shift. Yeah, steps is 25. So we can give it any number, but I think 25 is good. Anyway, so after 25 steps, how well does it recover? So okay, eval is this. So eval and training are, it almost was okay, equal to, almost, but not so close. But how well does it recover after 25? Goes down, then 25 goes down, then stays there, then after 25 it goes up, but it never really stays up. Goes down again, goes up, goes down, and then stays down, right? So it's the recovery. The recovery is a bit shaky. Like, it's not recovering so well, and also training is not doing a good job of training, because it's really just up and down. this is because of the shift in the regime, or maybe it's because of how the environment, the stationary environment. So we have to put that into factor, because when the environment is moving a lot or changing a lot, then system might also be in a state of trying to keep up with the environment. So that's why maybe we're seeing this, but we haven't really run for this for many steps. But this just tells us that we have still so much to do. And on reward, I think we can talk through these first. This is train was return episode return. So yeah, so training also not so bad. Okay, so the this is, so the dot, the small dots, this scattered dots is just the general like everything else. So, and then we draw the mean of that training, then we see like a curve that looks like this, and then we can do another the mean for the eval. It's not, it's almost getting to it's almost matching the training data, I mean the training steps or data or whatever this is. So yeah, so okay, this is, I think bad if it's, so we're still in the negative section. I think we need to get a little bit higher, and well, I'll have to see what the best value for this is, for the best value for returns. But as long as it's still negative, it just means that it just goes negative and then keeps going. It reaches at around points. Oh, sorry, this is minus 6.5. So minus 65 is where it stays, but we really want it to be, zero is good. Like if it's get to zero, then we're talking good. And the other thing is these plot components, reward components. I don't know what these sum towards. This is what blue is, sum reward distance, and sum reward control per episode, and then we have total return per episode. Well, I don't know how to interpret this. I think I need to. We can revisit this when we read through the prompt or the LLM's analysis. Then distribution steps, recovery distribution. So we can see that like these are how many, like how much it recovers. Is it? Yeah, on episodes only. So how much it recovers throughout the run in after every jump. So every jump, how much it recovers, and we can see this is the count. We can see the distribution so well. These are at the beginning. It's high. This is the count. How much percent? We can say 25. This is 25, maybe 30. Is it? What's the difference? 5. Let's say 20 something, 28. So 28 recovery. So that's how many it recovered during that point, that jump. And we can see here it's a lot, but then when it goes down, the recovery is quite minimal. It's not a lot of recovery, and we will see these analyses in the response for LLM. And then so let me just This is the latest, I think. So yeah, this is the latest, and this is the same data I just plotted using this. So I will. Okay, let me see if we can go through these. So episodes. Let's open episodes first. Episodes in open from data runs and multi-agent 67, and we want episodes. Episodes, and we also want, let's open this one at a time. So this is the data, and okay, is evaluating. We can see is eval is a Boolean value, so it's 0 or 1. When it's 1, we are doing evaluation. When it's 0, we are in training. That's and then every 25 steps we do eval. I think 20. Every 20 we do eval. And steps in episodes always 50, and then distance is measured. Then we have mean distance. We have success. Success is 0 and 1. And terminated, none is terminated. Okay. All right, so we can check regime change. Apparently regime change is never changing at all. Maybe, okay, just strange. But regime ID, we have regime ID. I think this is using chaos for some reason, not the regime change. Okay. All right, so let's read this. Let's read what it says. So eval, logs, adaptation, config, sanity check, training. Train episodes is 400 because we have 50 of them. So 20,000 divided by 50, we get 400. So these are how many episodes we use. So 50 is coming from steps in episode, 50 steps each. And then eval episodes, 20 eval batches times 80. 8 is 8. What is 8? I think 8 is not sure what 8 is. What did we set 8 to be? Number of episodes. Okay, number of episodes, and every episode is 20. So we get 20 times 8 to get 160. Training steps. This is exactly 20,000. Eval is clearly separate. Okay, so this is just telling us what we have. So the performance is training and eval. Training is 400 episodes. Eval is 160 episodes. It says mean return is, we saw this, mean return is minus 65, 66. I don't think I can get, let me find this. Okay, so I'll just enlarge this so we can see it clearly. So here is what we are, minus 65, so we are at this point. And then success over ever reached threshold. Threshold is 0.05, so those that reach threshold is 28% success mean, and hopefully we have that in here? Yes, we do. So this is the graph that we're looking at. So so the calculation is based on 27 is the mean. So the mean is eval mean is the green one. So the green one, how many reached threshold? The threshold is 0.5, which is here, 0.05. So only, I don't know, 1, 2, 3, 4, a bit of them, 27 or 28%, ended within threshold, 6%. So not so many ended within threshold. Others are above, or others are quite, or those that are within threshold are just, those are below the threshold. Those are what we're talking about as 6.2%. 6.2% of all of them, all of those that are within the threshold. I mean, the final success. This is quite bad. We are really doing bad. Then median distance. So we also saw distances. I think this was this, yeah. And median distance, what we're talking about, this median is the green one. It's 0.112, and then median final is 0.179. 0.17, which is the final one, is the red one. 0.179. So it's the median of these somewhere here. Okay, and then we can eval episode. So this is for training. We're looking at the training actually. So okay, training is here, and training final is this. I see. Okay. So eval is the same story, -6.5. Not so bad, not so different. And then success is 71%. So 72% threshold were above threshold for success. So the graph for success is this 71%. And after the run, so after the run is success, I mean the final is 10%. So a lot got to recover, but then a lot got to stay, less got to stay in the recovery zone. So not so many stayed in the recovery zone. So 10% is a small number. Then median, small numbers. Now the big pattern, touch and go behavior. So this is what okay, so let me just read this. So this is the single most diagnostic thing in the run. Train 21% of episodes reached the target at some point, but it did not finish close. Success main is 1 and success final is 0. And I think this is from this data, success final and success mean. So success mean is 1 and then success final is 0. I think it's taking the mean of this. And let's go on. So no. And eval is 61% of episode did that. So the agent can often get near the target, especially on eval. But it frequently drifts away by the end. It's doing flybys. Okay, so helpful drift measure final minus mean distance, and we get this for training is 0.026, and for eval is 0.098. And that's why mean distance success looks great on eval, but final success does bad. because this is too high. Which eval targets are working? Okay, we have 75% success, and yeah, this is a strong hint that either holding position isn't incentivized enough by reward, or their dynamics overshoot oscillation, stop acting to save control cost. Yeah, I think so much here is just talking about, okay, so from the per step logs aggregated per episodes, yeah, I think we need to know which of these, because if we just know between, if you subtract success mean but near zero final, so success mean near zero final, success final meaning the controller reaches them but doesn't stabilize enough. But yeah, so I guess most of this is just due to like the system doesn't stabilize enough. Let me just see from this previous one. I don't have it. Just for us to understand how this the LLM is reaching to the conclusion. So we need this lab. Which lab is this? 60 something. 60. Is it 60? I don't know. It's 60. We want 67. This is just for training. It's not for evaluation. I want to check for stability. This one. Stability. Still running, sorry, give it some time. Wait, what? No, what? What happened? Did I, oh, I see, there's nothing. No way. It's supposed to show something. Coherence is 0.99. That's not right. Okay, I'm missing something here. Log file. Wait a minute. Which one is this? Okay, I think something changed in the code. Let me run this first. And then do this. Oh god, okay, so something is not right here. can't debug right now. Oh, I see. There's one piece of code I need to run. This should be in the same section. Run this. Okay. Let's see how we're doing great here. Any charts? Okay, so Niraj, thank you for coming back. So I'm a programmer, mainly Rust, but share a list of topics I should learn if I want to understand all of this stuff, or maybe get into building this algorithm myself. Can you share a list of topics? Okay, yes, I can. Yeah, I can share some of the topics you can explore for this stream, and then yeah, one moment, I'll do that in a moment, and let me try to I'll just talk about what the topics are in the system, like what we are using in the system currently, and how we have implemented them, not how, but just how they are used in the system and how they drive the system from training to like evaluating currently. And then this is good for like everyone who is interested in the system and has not gone through or has not really seen or began with us when we were starting this. But okay, it seems like something is not right. I think it might be the data, but let me find out why. I don't want to debug this right now. Maybe it's data issues. Okay. Yeah, definitely. Let me just keep going with this. Decomposition, dominating returns from the per logs. Okay, ideally what it's saying, the system is it's never recovering so well, and this is due to like non-stationary behavior of the system, and then training in an environment that is always shifting. Every other steps it shifts, but at the end, generalization split, partially visible but not end to end. So the results it plots. Okay, I showed the plot, so we don't need to go through these. The most actionable takeaways is the agent can often reach but not hold. This is because of the, I'll say it again, it's because of the regime non-stationary environment, shifting the environment all the time. And once we have figured out how to keep it, or maybe we can do it, we can run it for many steps, but once we get to the point where the system can hold that position, it's doing good, keep it that way. We can use reinforcement learning. It's already inbuilt. I think it's a good way to explore reinforcement learning in the system in a way that when we are doing good, we should hold that position and never go down. If we go down, we get punishment for that. So eval shows this brutally. So 71%, 72% reached at some point. Only 10% finishes there. That's not good. And we want to get to a point where when we get to 72%, then we should stick to 72%. When we go down, then we get a punishment for that. So that's basically reinforcement learning. Then return is dominated by control penalty, and control cost gets worse over training that can incentivize stop acting once close. Then adaptation stroke generalization instrumentation is present but inconsistent with the core episode success metric. So the threshold episodes, and I think dynamics randomization isn't measurable through logs because parameters are not. I think this is talking about some field. Is it which field? These two, maybe. And then ideally what we just need to figure out is reinforcement learning. So one of the things we can do, we can try to figure out is how can we keep it in a way that how can we keep the system in a state that it holds when it's doing well, or it's either hold or go up, hold or go up. And once you're up, don't go down. I mean, you can go, if it forces you to go down, don't go down, then, stay down. You have to improve, keep improving. So that's one thing we can explore next. And then, so before we, those are the results. We want to go to the code wise, to code section, and walk through the memetic idea, because I think one thing we can really measure how successful each agents are, because we just measured one agent. Now suppose we do it for multiple agents. This is a good point or position to talk about multi-agent and memetics, and also a good point to introduce what we call evolutionary or evolution in this case. And evolution is one of the way we find the best rules or the best genome. So that's one of the ways, but it takes so much time to run, so I won't run it here. Maybe I will do some background run or on my own, and then we can explore the best genome at that point. But keep note of this genome right now. It's what we have, right? I ran this for a while back, the last evolution I did. But so that's it about the test or the data and the results. And next step is figure out how to keep the system always keep the system in that position or recovery state. So we can talk about recovery. I don't know if there's an idea called recovery, adaptive recovery or something like that. Recovery in is it ML? I don't know. Recovery strategy, where we have adaptive recovery in ML involves using ML to dynamically adjust system responses to failures. That's basically just reinforcement learning, right? Changing conditions, allowing for self-healing, proactive fault detection, and penalized rehabilitation. Moving beyond static fixes to learn from data and optimize recovery in real time, whether it is data centers, software, or patient therapy. So we can explore this idea. It looks like people are also talking about recovery here, recovery strategies, AI and ML in data system resilience. But I think This is more like data centers or something. Autonomous self-adaptation. Okay, what is this? Security. Research gear. I'm not a robot. Okay, self-adaptation in the cloud. ML's Hills framework for proactive fault detection. So this is the next research area or research research step or research quest or something like that we can explore next. Artificial intelligence and machine learning in motor recovery, deep codec, adaptive sensing recovery. All right, okay. So mimetics. Let's see. Oh, okay. So Niraj, back to you. I think I can take a few time to talk about. This is for everyone. Talk about the ideas, and I'll just note them in this document so that we. So the question was share a list of topics. Yes, of course, list of topics. Topics in the system. So first, I think dynamic systems. Topics. Let's make this bullet point. Okay, so dynamic system. So dynamic system is one of the topics we are talking about, and dynamic systems. I can look it up, not look it up, but just give you a sense of what it is. So dynamical systems. The brain is one of one of those dynamical systems that are mostly studied in brain science. We also have the weather is a dynamic system. We also have algorithms. I don't know if that's true, but in physics we also have what is this? Lorentz attractor arises in the study of oscillators. So dynamical systems is a system in which a function describes the time dependence of a point in an ambient space, such as a parametric curve. Example include mathematical models that describe the swinging of a. So this is more like physics, but it's the same idea. Like dynamical systems are systems that change in time. They keep changing in time. So that's one of the ideas we have, and we are using dynamical systems. Like generally, like the entire system is built on this idea, and I can open a few dynamics. I think I have. Is it dynamics file? Yes, I do have dynamics file, and I do have type as well. Jesus Christ, I think. Types. What is happening with this? Okay, so dynamics. Dynamics is just the environment, how it changes. So we're using the environment to detect dynamics, and we this is just one of the ideas we're exploring. The other one is adaptation. So adaptive systems, or adaptation. Is this right? Adaptation. Adaptive systems, adaptive, predictive coding. So so every title of my stream, we have this adaptive predictive coding, and that means is just we are trying to build a system that can adapt and do predictions well, right? And we connecting all these ideas together to come up with an adaptive system, an adaptive predictor. And that's just one of the idea we are exploring. And then we have this idea of meta learning. So meta learning is a concept that is known by many who study learning in machine learning or learning in people learning. So meta just means learning how to learn. So if you have a system, which we do, right? And you want a system to online learn or to do an online learning, which is also one of the stuff we have explored, like recursive online learning using recursive least squared. So if you have a system that you are building for online learning process, you want it to learn online, most definitely you will have the concept of meta learning in the system. So meta learning is how does a system learn how to learn so that it can do an online learning process. It keeps learning throughout the system as it adapts. But so as it adapts or as it works throughout time in the system, it has to learn how the system works or how the environment changes. Is it changing in a specific way that I should also be changing in another certain way so that I can keep the environment in consideration every time I do learning? Because learning is one of the major things that we are focusing on in adaptive predictor, so or adaptive controller. So if a system can learn online, then it has to also know how to learn when it's doing online. And from our system, we have this concept or idea of tuning the system while it's doing some sort of learning, and we call those tuning process meta tuner. So meta tuner is just it controls how the system does learning. So if it's doing well, if it's above threshold, if it's doing so bad, is it consuming energy? Is it supposed to learn? So meta tuner just controls that. And then we have meta layer. Meta layer is another idea we have explored, or we build it into the system. So meta layer is let me find it. It should be somewhere. Let me just search this. So meta layer is our system is it's composed of so many plugins. It's composed of so many things we get from different environment, from different agents like memes. It's composed of that. But where do they meet? And how do they interact when they meet? So that our meta layer is just doing that, and then does also compression. So compression is because if there are so many things coming together, it just means that there's so much information going around from one place to another. So compression is good. It helps to compress a lot of information or big information into simple, in our case, 2D. Is it 2D or 1D? It's 1D information code compiled into 1D, and then that information can be used as a genome, or can be used as a measuring values or rewards values to measure while doing rewards. And from these, I think I can add this compression compression. Data compression is one of the main topics. If you can, like, intelligence is just compression. You know, if you can compress a large amount of information into, let's call it lossless compression. Lossless compression is compress information in a way that doesn't you don't lose the information. So lossless compression is a concept of compressing information without losing information. Data compression method that shrinks files, not just files, but just generally information without losing information. Now that's also one of the things we have, or you can explore. And maybe I should add recursive list square. This is an online learning algorithm. Can't type. Right, and going on. So in our system also we have a way of detecting. So as I've talked about this so many times, we do some sort of detection. You know, run our models in a regime that changes all the time, or in a non-stationary environment. So non-stationary environment is an environment that changes every other time, every time. Non-stationary environment. And so when you have a system, that is running in a non-stationary environment, a good way, or one logical way to keep it in check, or to keep this model always alert. You know, I want to be alert in this environment, is to detect these changes, or to detect some of the changes in the environment, to detect noise, or to detect when the environment changes, or when the environment becomes too chaotic to survive. Because if a system does not have that detection mechanism, it breaks, right? We see this a lot in data centers. When, you know, data centers are a good example of detection. If you have a system that has a good detection algorithm in a data center, then you can detect when something is wrong in the system. Maybe the cooling process is down, or something else is that might lead to, you know, you losing data, right? So we need a detection scheme, or a detection mechanism. And for us, for this case, we are using this page Hinkley algorithm to do detection in Hinkley detection. Let me just type this before I finish my thought. So we are using this to do detection, to detect when an environment changes, when something changes in the system, when the model needs to be learning, or something like that. So we do regime changes, or detection algorithm. Yes, so this is another one. And then let me just search it. So this is one of the algorithm we use to do detection, to detect when the system changes. And I could show you an example of this in the code. So for say we have in a kernel, we have the kernel, we do have what we have chaos somewhere. Hopefully, yes, we do. So chaos, here. So this is where chaos is computed, right? Now, to detect when a system is chaotic, I think let me just find the example of using this. Is it predictor? I think it's in predictor page what? PK. I don't know if it's here, but page what? Hinkley. Is it here? I don't remember where I put it. Should be in health. Let's try health. All right, I can find it. But yeah, so the idea is you need a way to detect regime changes, and when you're dealing with environments like creature, it's a complex real environment. You have to detect when something has to tell the system, you need to be doing this, you need to be learning, or stop learning a bit and then continue. And the other thing we have in our system is this cultural exchange. I think it's not a bad idea to explore. By the way, it's a good one. Mimetics, cultural evolution. This is if you have multiple agents, running in the system. This will be evolution, and you can. So this idea comes from this book, nice book by Susan Blackwell called The Meme Machine. Nice one. And then we have who is this? Susan Black. Hopefully I spell her name correctly. But, yeah. So and then we have also another one is from Selfish Gene. What? This guy, Richard Dawkins. Hopefully I get their names correctly. Dawkins. All right. Okay. Right. Let me stop there. Right, and then the next thing I think we have explored is which one is this? What have we also explored? Meta learning is captured. Oh, adaptive evolution. So adaptive evolution is one big one. So adaptive evolution is you have a system and you can do some sort of random mutation to the system, or to the rules to see how the system behaves. Does it behave like you expect when you initially start with a specific number of rules, the initial rules, or the initial genome? When you keep changing the gene or the rules, does it become better or does it go even worse? So that is this idea of the adaptive evolution is also built in the system. So to see how the system ends or behaves or does or learns, or in our case learns, behaves. I can't write behaves. Adaptive evolution, and I can show you an example. We have evolve right here. Evolutionary knob search with shared environment. So fairness per generation. run the system in generations, right? You have generations, you run it generations, keep running for each generation. Every generation produces a good elite gene, then that it's propagated to the next generation. Keep running like that, doing mutation to the system, and I think mutation is also included here. So mutation is just compute the fitness of the of the current genome, or the current gene, and then the best fit, which I think in adaptive evolution terms, the best fit is the one that shows better improvements, right? If you are a parent and you produce some sort of genes or children, or let me just use in a code. If you run a code, the code initial genome or initial rules, which is this, is interpreted as the parent genome, right? Or the parent rules for the system. Now you evolve that, you adaptively evolve that gene, this gene, to find the best of this gene. Now to compute fitness for this gene, you have to just find, use the previous genes, or if you have you run multiple children from parent, the same gene, you get the best fit from all those children you run from the parent genome. Then once you get that, once you have a best gene or a best genome, you evolve that again, keep doing that until you have the best of the best, right? Until you stop, because a threshold to stop will be just you get cut off. You can cut off. Maybe you want to stop after 1,000 steps, then use that genome to evolve. So adaptive evolution is one of the ideas we have explored. The other one, hopefully I'm not forgetting, is so neuroplasticity is another one we found recently. I think we have been doing this for plasticity. So neuroplasticity is from the world of neuroscience. From the world of neuroscience, it's an important concept that I think people should really explore, and also look into Hebbian learning, because Hebbian learning is something in connection with plasticity or synaptic plasticity. So these three, synaptic plasticity, synaptic plus TCT. Plasticity just means how flexible, the strength, like plasticity is the strength or weaknesses of connection between neurons. And then Hebbian learning. So with this, all these, Hebbian learning is important. So Hebbian, how do you write Hebbian? Hebbian learning. So Hebbian learning is a type of learning in neuroscience for connected neurons. So if the so let me just learning is a neuroscience principle summarized as neurons that wire together, meaning when one neuron repeatedly helps trigger another, the synaptic connection between those two strengthens, right? So it's once it strengthens, then learning becomes better in that case. So Hebbian learning is one important concept we have explored in the system. And then one other thing is wait, what other thing we have done? Okay. Oh, so in this case, the idea of energy, like energy, I think it's called free energy principle. Like the whole idea is just to do research in this area, not to build some, like we are doing research while building. At the end, when we have gathered as much information as possible, then we can, analyze what we have. So free energy principle is one of the, it's a theory. Is it a theory? It's a theory. But in our case, what we are talking, when we talk about free energy principle, we are not saying that there is free energy. We're just saying that a system has to make sure it uses whatever energy it has to a minimum until it gets to a stable position. So you have energy, this energy is minimum. How can you make use of this energy, right? It's, so that's just basically how we are doing in the system. And we have energy fields. I talked about this a long time, a few times back. If I can get one thing to open here, then I can show you, but I don't know why everything is broken. 59. I don't want to debug this right now. And any charts? Oh, so I tried watching previous streams. It's difficult to understand. Okay, so Niraj, I apologize. I have not put out materials to do some learning, because ideally what I'm doing is just doing research on a go, not sort of writing anything. I just do research as I go. But if I get some time, I think I'll compile some of this information into one good PDF so that you can follow along, and then so that you can follow along, and then so that we keep this process going. Because as far as where we are right now, we have covered a lot in previous streams, and we're still going, because the end goal, we have a goal. We haven't even reached to a point where we need to build a cellular automata and all that good stuff, and also how to involve those rules. Actually, let me also include that to our our list. So cellular automata, specifically game of life. Yes, so yes, I understand, and when I get some time, I'll do that. Create some PDF or something, some other way to do that. Then where and what and where are you are the environments where you test the agents, right? So the environment I'm configuring. So right now first of all, we started with a toy environment, so let me just show that. So we have environments. Let me find the environment config. So these are the environment we have. So when you have a specific environment in mind, you can just change these. I just change this to that specific environment. If I'm running on toy environment, I'll just say name is equals to toy. But now I'm using Richa. So Richa is an environment for testing control. How can a system control itself in an environment like Richa? So when it comes to environment wise, I'm using Richa. Up to this point, I've been using Richa, but we have, the goal is to also use cellular automata as the test bed environment. And why cellular automata? It's because of this idea called neurocellular automata. I can type, man. Neurocellular automata. Like, okay, so if you have been on this site, then you will, I will just paste this somewhere. If you have been on this site somewhere along, you would so you will see many different ways of playing with a CA, and this is a good material to explore, like how if you do some deletion, the CA just manages to remember its memory, like its memory idea, like, but then what the hell, it remembered but then created some alien thing. You delete its tail, it just regenerates again, keeps doing that. The idea of memory, right? So we can try new one, refresh, delete the tail, it generates, delete again, it generates, delete the head, it regenerates. So cell regenerative algorithm. So what we just want, in short, if we have if we can build a cell regenerative algorithm using a CA, we can test things like this, how like CA manages to remember things or to regenerate its cells, right? That's one of the end goals. So as far as environment is concerned, CA environment will be the next thing we'll explore once we have a stable system. Now we are just using richer, and then I think that answers the environment question. And let's see what's next. Let me just post this again here, and let's see the other question. Also, what about memory? Also, after an agent has learned something useful. So after an agent has learned something useful, we are keeping that something useful as a compressed version of its code. So in our system, I remember we talked about compression in our meta layer. Where is meta layer? Is it here? So we do compression of whatever the agent has learned. And oh my god, what's happening with my editor? I need to figure out why this is happening. So memory in connection with compression, we get memory, right? Like we get a system that remembers somehow, but our system is not robust in a sense that we remember as far, like a lot, like we can't remember many steps. We only have just, I don't know, k steps, that's k equals to 2 or 1. We can only remember as far as that k, the k value, and we go like 1 step, 2 steps, 3 steps. We can't go farther away. And our way to remember is, although we haven't figured out how to make memory work, like this, I think we talked about plasticity gating, because that's just like one of the way we have managed to keep memory in check so that the system doesn't forget a lot. And learning rate also, we explored the learning rate. So let me just add this plasticity getting as a way of, was it event modulated plasticity? Plasticity. This helped us in the forgetfulness problem we had before. So when the system was forgetting a lot, let me helped in our model forgetting what it has learned. And we learned that this was due to maybe a higher learning rate or higher order, because we had higher order predictors. So higher order predictors, if we had maybe 4 orders, but our learning rate or our predictor is using just 2, then we get a padding of 2 zeros at the end to make the system, or to fill up the system, which makes the system forget, right? So that's one solution we got. We used plasticity getting as a way to solve that. And now we have a system that runs and doesn't forget. Okay, the other thing is memory. Is in terms of memory, I've already talked about compression. Do some compression and then serve that compression to other maybe agents, but plasticity getting was one of the major things we tried to solve using memory, the memory problem. But this is just for the test. We haven't really tested it in an environment where we can see then the system do learning as it remembers. And then context, another thing was context getting. And context getting was mostly it relates to plasticity getting, but it's more of we get based on what we see, or what the environment feeds into us, like the context of the environment. So that's one thing we explored. And then I guess that's all about. I can keep going. I think if I remember some of the things we have talked about, or we have learned, or we have explored. Yeah, so let's see. Equilibrium, retractor, regime. Oh, so this thing called self-tuning nervous system, I think it's just a fancy name, but self-tuning self-tuning nervous system is what we currently have going on here. Like nervous system, Jesus Christ, I can write. Okay, so self-tuning nervous system is what we have going on here. Like it's a plugin we put into the system, and then it does self-tuning. By self-tuning, I mean you get to a point, the system is performing so bad, or it's maybe it's above threshold. For example, if it's energy, then it self-tunes itself, or just fine-tunes itself, in the sense that it gets to an equilibrium state. It wants to keep that, it wants to be in the good state, right? So it does self-tuning process. Okay, so the other thing is, let me just keep going. So the other thing is, I don't know, I feel like we have a delay in the live stream. Is it my connection? Yeah, I think it's my connection. It's so bad. Oh man. Okay. All right. So let's see. Let me try to solve this. Okay, let me try to solve this. Okay, so yeah, so I think if we are in good shape, I should have all this information. Hopefully, maybe can I paste? Can I copy these? I don't know. No, I can't. Can't chat that much information. All right, so for those who joined us, thank you very much, and thank you for learning with me. I know that there are a lot of topics that I haven't included them here, but there are quite a lot, and they are good to help us, learn as we go. And thanks for the starts, for the questions, and I think see you next time. And bye bye. Yeah. Okay. And